Now let us move on to reading 11, hypothesis testing. Under this LOS, we will look at the definition of hypothesis testing, the interpretation of a test statistic, type 1 and type 2 error in hypothesis testing, the significance level and how they are used in hypothesis testing. Then we'll look at the decision rule, power of a test, and we'll look at the relationship between confidence interval and the hypothesis test. Then we'll understand what is the difference between a statistical result and economically meaningful result. We'll understand the significance of p-value and how it is related to the hypothesis testing. We'll look at the identification of appropriate test statistic and the interpretation of the results, where we are comparing two population mean. We'll take both the cases where the variance are known and where variance are unknown. Then similarly, we'll find out the appropriate test statistic for the cases where the variance is unknown and we are assuming that variance of both populations are equal, and in the second case they are unequal. We will find out what is the appropriate t statistic for these cases. Then we'll find out the appropriate test statistic in the case where we have two normally distributed populations and we are doing a paired comparison. So there are a specific test for that, we'll find out. Then we'll identify the appropriate test statistic and the interpretation of the result for the cases where in the first case we want to compare the variance with a number for a normally distributed population, and in the second case we are comparing the variance of two normally distributed populations. So there are different tests for these two cases. We will look into them. And finally, we will try to distinguish between parametric and non-parametric test and the situations where each of them is applied. So now let us start with the definition of hypothesis testing. So this comes under the branch of statistics, which is inferential statistics or statistical inference. Hypothesis testing basically comes under inferential statistics. They are basically two parts. One is estimation, another is hypothesis testing. In both these cases, we try to infer from a sample about some characteristic of a population. For hypothesis testing, suppose we have a large population P. We want to ascertain certain parameter of this population. So one way is estimation using sample, and the another way is we have a sample, we have certain sample statistic from the sample, and then we want to make a hypothesis about the population regarding certain characteristics of the population, and then we test the hypothesis. This comes under the procedure of hypothesis testing. This can be concerned with one population or more population. We can even make a comparison about the characteristics of two population using hypothesis testing. Hypothesis testing helps us to find out whether a claim about the population is true through sample. For example, there is a large factory which is producing say 10,000 product daily. So our population size is 10,000. We have taken a small sample of say 100, which says that there is only one defective product out of 100. There is only 1% defect. But we do not know the same thing is true for the population or not. So for that we need to perform hypothesis testing, where we are claiming that the default or the defect in this case is just 1%. So we need to check whether that is true for the population. The way we start hypothesis testing is with forming a hypothesis. One is alternative, one is null hypothesis. Let us explore what they are. So the alternative hypothesis is the one for which the researcher wants to gather supporting evidence. And null hypothesis is the one which the researcher wants to reject, or he wants to gather evidence against it. So through statistical tests, we can never accept a hypothesis. We can only either reject a hypothesis, this is first case, or there could be another case where we do not have sufficient evidence to reject. So to the second case, we cannot say that we are accepting a hypothesis. We will always say we do not have sufficient evidence to reject the hypothesis. For example, if in the above case, from our sample, we know that the defective piece are 1% of the sample, and from this sample, if we are estimating for the population and assuming that there should not be more than 2% defective pieces in the whole population, in this case, our alternative hypothesis will be the defective pieces mean should be less than 2%, and the null hypothesis automatically will become mu is greater or equal to 2%. So with some confidence we should be able to say that the defective pieces in the population are less than 2%. So there could be only two cases, one where we are able to reject the null hypothesis if we have sufficient evidence to reject this hypothesis, then we can say that the defective piece in the whole population are less than 2%. There could be another case where we are not able to reject this null hypothesis. In that case, we are not saying that in the population the defective pieces are more than 10%. We can only say that we do not have sufficient evidence to reject this hypothesis of defects more than 2%. Now let us look at the steps involved in hypothesis testing. First, stating the hypothesis as we have just looked, which involves choosing the null hypothesis and alternative hypothesis. The second step is choosing appropriate test statistic. This is based on the population parameter which we want to assess. So it could be Z statistic, T statistic, chi-square statistic or F statistic, etc. Then third step is to specify level of significance. We know level of significance is alpha, which is 1 minus the confidence level. For example, if we say level of significance is 0.01, that means we are 99% confidence of the outcome. The fourth step is stating the decision rule regarding the hypothesis. In this, we decide what are the critical values on which we decide to reject the hypothesis. Next step is to collect the sample and calculation of the sample statistics. Sixth step is making the statistical decision regarding the hypothesis. This is based on the test statistic and the critical values, whether we are able to reject the null hypothesis or not. And finally, after the statistical decision making, the last step is making the economic or investment decision based on the statistical decision. It is always related, but it is not certain whether statistical decision is translating into economic decision or investment decision. So certain other inputs are involved here in the last step. Now let us look at the formulation of hypothesis. It can be done in three different ways based on the premise which we want to test. One way could be where we want to prove that something is not equal to a particular value. Here not equal to is going to be alternate hypothesis and null hypothesis is going to be equal. The cases where we want to say that value of a particular parameter is greater than certain number, so that will be our alternative hypothesis. Accordingly, null hypothesis is going to be theta less than or equal to theta naught. So this is a numerical value, this is our parameter. And on the same lines, there could be third way in which we want to prove that theta, the parameter, is less than a particular value. There we have the opposite null hypothesis as usual, which is theta greater or equal to theta naught. Now if we look at the first case, we have to do two-tailed hypothesis testing in this case. Since we need to conclude about both the tails, we are just analyzing whether theta is not equal to certain value or no. So both sides we have to say if it is less or if it is greater. In the both cases we are able to reject the hypothesis, which is they are equal to each other. So in other words, we can say we reject the null hypothesis in the favor of alternative if the evidence indicate that the population parameter is either smaller or larger than the coefficient. Now if we look at the second and third case, here we need to conduct only one-tailed hypothesis testing, since we are talking about only one side of it. Say if the alternative hypothesis is theta is greater than theta naught. So this is the only thing which we want to prove, that theta is more than certain number. So if it is more, then we will be able to reject the hypothesis that theta is less than or equal to theta naught. We are not worried about the other side or other tail. So this is one-tailed hypothesis testing. Now let us move to the next slide. Selecting the test statistic. Based on our requirement, we need to find out what is the statistic we are going to use. As we earlier discussed, there could be t-distribution for t-test, standard normal or z-distribution for z-test, chi-square test for chi-square distribution, and f-test. The broad formula for test statistic is the value of sample statistic minus the value of proportion population parameter under null hypothesis. For example, if we are comparing theta with theta naught, this theta naught is the value which will come in the numerator this side, divided by standard error of sample statistic, which we know is going to be sigma by root n for z and t-test. T-test sigma will be replaced by s, since the sample variance is known and the population variance is not known. Now let us move to the next slide. Here we understand the level of significance, which we know is represented by alpha, and it is given by 1 minus confidence interval. For example, if we want to be 99% sure, the value of alpha is going to be 1 minus 0.99, which is 0.01. This is our level of significance. We need to decide what is our level of significance before we can conclude about the outcome of hypothesis. So once we have calculated the test statistic, we can either reject the null hypothesis or do not reject the null hypothesis. So the decision is arrived by comparing the calculated test statistic with the specified value, which is coming from our level of significance. This value depends on level of significance, which reflects the sample evidence required to reject the null. For example, as we know, for 5% significance level, the value of z statistic is 1.65. So this is the critical value which we are going to compare with the test statistic in order to conclude the outcome of hypothesis testing. So there could be 4 possible outcomes when we are testing a null hypothesis. The first could be we are rejecting a false null hypothesis. So this is a correct decision when we are able to reject a false null hypothesis. Another case could be when we are not rejecting, we are not able to reject a true null hypothesis, where the hypothesis was true, but we could not find sufficient evidence to reject it. So again, this is a correct decision. So first and fourth are the correct decision. Now there are two other possibilities where we can make an error. First, where we are rejecting a true null hypothesis. The null hypothesis was true, but we could collect sufficient evidence to reject it. This is an error. It is called type 2 error. Similarly, there is another case where we are not able to reject a hypothesis which was false. Again, we are doing an error. This is called type 2 error. So this probability of committing type 2 error is also known as the power of the test and is represented by beta. And as we know, the probability of making type 1 error is level of significance, which is denoted by alpha. So if we are saying alpha is 5% or the confidence interval is 95%, that says there are 5% chances of making type 1 error. There are 5% chances that we are rejecting the hypothesis while it is true. Now let us move to the next step, stating the decision rule. When we are testing null hypothesis, we calculate the value of test statistic. We have already seen the formula. So we generally take a higher extreme than the given value, which are to be put in hypothesis testing. There is a specific level of significance alpha which we have determined. So if we have statistically significant difference, we will be able to reject the null hypothesis, and if evidence is not statistically significant, we are not able to reject the null hypothesis. These are the two possible outcomes which we already talked about. So the values which we are comparing to calculate test stat, and then we make a comparison between the value of test statistic and the critical values, which are also known as the rejection points. Based on the comparison between these two, we will reach the conclusion about the null hypothesis. For a two-tailed test where we are comparing both the ends, the null hypothesis is say A equal to A naught and alternative hypothesis is A not equal to A naught. This is a two-tailed test where we are testing both the tails. The critical values which are used are indicated by Z, where we are using Z test, alpha by 2, and for one tailed test, the critical values are going to be Z alpha. Let me take an example. Suppose the level of significance is alpha, that is 1%. So for 1% level of significance, we know confidence interval is going to be 99%. So if we plot the normal distribution curve, this is the center point, mean, mode and median, and say this area is going to be 0.99, which is the probability, whereas these points are minus from confidence interval 99%. We can find out that these values are minus 2.58 sigma and plus 2.58 sigma. This is for 99% confidence interval. So in this case, we know the value of probability on the left hand side tail is 0.005 or 0.5%, and on the right hand side also it is 0.005. That is why the summation will be 0.01 on both the tails. So if we are talking about two tail test, the statistic which we are talking about is Z alpha by 2, that is Z 0.5%, which will be minus 2.58 sigma in this case. If we are talking about one tail test, then we'll find out Z alpha, which is Z 0.1, 0.01 or 1%, because in that case we are looking at only one side, like this. The complete area is going to be 99% and 1% is going to be on the right hand side tail. Now let us move to the next slide. Here we are taking an example of hypothesis testing. We have taken a sample of 40 sales receipt from a green store. So number of elements in the sample are 40. The sample mean is 137 and sample standard deviation is 30.2. Now using these values we need to test whether or not means is different from 150. So that is our alternative hypothesis. Mean is not equal to 150. Automatically the null hypothesis is mean is equal to 150. So if we are able to reject the null hypothesis, we will be able to say that the population mean is significantly different from 150. It is not 150. So let us calculate the Z statistic first. We know from the formula it is x bar minus mu naught divided by standard error, which is sigma by root n. So value of x bar is 137. Value of mu is given as 150. That is what we are using here in our hypothesis testing. Standard deviation is sigma of population, which is 40 is the number of elements in the sample. Here we are assuming that this standard deviation is given to be for population. This is population standard deviation, sigma. So value of sigma is 30.2. So we will get the z score, which is minus 2.722. In case the standard deviation had been for sample, we will use t test, and instead of sigma we will have s here. We will use the same value. The value of t statistic is also going to be the same. The only difference is the value which we will get from the t distribution table in that case. Here we are using z statistic. Now let us see how do we use this information for the decision making. So in order to make a decision, we need to finalize what is the level of significance, alpha. So let us say in the two-tailed test, we have decided that alpha is going to be 0.01 or 1%. Our confidence interval here will be 99%. So let us calculate the value of z score for the value of 0.05 of alpha. Since it is a two-tailed test, we are using z alpha by 2, that is z 0.005 or half percent. From the table we get the value of 2.58. So now let us compare 2.58 with the test statistic. So this is our critical value, which should be compared with the test statistic, which was 2.722. We have calculated it in the last slide. And the comparison says 2.722 is more than 2.588. Since the sign was negative, so it is going to lie in the left tail, which is our rejection region. We can clearly reject the null hypothesis in the favor of the alternative hypothesis. Since our test statistic is more than the critical value in absolute terms, we can reject the null hypothesis. In conclusion is, the mean is significantly different from 150, which was our alternative hypothesis. Now let us take one more example. Your insurance company is reviewing the current policy rates. When original settings, the rates they believed that the average claim amount was 1800. Now they are concerned that the true mean is actually higher than this. So this is what they want to test, because they could potentially lose a lot of money. They randomly select 40 claims. So number of elements in the sample is 40. They calculate a sample mean which is 1950, assuming that the standard deviation of the claim is 500. So this 500 is for the population. The level of significance for the test is given to be 0.05 or 5%. So based on this significance level, we need to find out the critical values, and we are testing if the assumption which the company is making is true. That is, whether true mean is higher than this 1800. So that should be our alternative hypothesis, that true mean mu is greater than 1800. Yes, this is our alternative hypothesis. Automatically the null hypothesis becomes mu is less than or equal to 1800. Now let us move to the next step, which is the calculation of test statistic. Since the variation is known to us, let us use Z statistic, which is x bar 1950 minus mu, which is 1800 from here, the value which we are using for the comparison and hypothesis, then sigma 500 and n, which is 40. From that we get the value of Z, which is 1.897. So this is our test statistic. Now let us find out the critical value of Z at this significance level 0.05. In this case we are talking about one-tailed test. So we use Z alpha, that is Z 0.05. This value is 1.96. So we are going to compare this value with the test statistic. Clearly the comparison says that critical value is more than test statistic, which is an indication that we are not able to reject the null hypothesis since our critical value is more than the test statistic. If we look at the graph, so this is for one tail test, the right tail. This is the critical value 1.96. We are comparing the test statistic with this. Our test statistic value was 1.897, which falls on the left hand side of this critical value. So we are not able to reject the null hypothesis since it is not falling in this rejection region. It is falling on the left hand side of the rejection region. So we failed to reject the null hypothesis. We cannot conclude anything statistically significant from this test. So we are not saying that value of mu is less than 1800. The only claim which we can make is we do not have sufficient statistical evidence to reject the hypothesis. Now let us move to the next slide. Here we are comparing the confidence intervals, hypothesis test. Here let us look at the use of confidence intervals in hypothesis testing. As we already know that confidence interval is the range of values within which we believe that the value of population parameter will lie. As usual, the confidence interval is going to be the sample statistic plus minus the critical value alpha or alpha by 2 based on one tail or two tail test into the standard error, which is sigma by root n. Let us take an example to clarify it. The question says construct a 95% confidence interval for the first example and decide if null hypothesis should be rejected. Now let us look at the first example and take the values from there. This is the first example. We know the value of test statistic is minus 2.722, value of n is 40, sigma is 30.2. Let us put these values there. The standard error is again 4.78. The sample statistic was 137. Now let us find out the critical value at 5% significance level. We know this is a two-tailed test, so we'll take Z 0.025. Alpha by 2 is 2.5% or 0.025. The critical value is 1.96. From our formula, we can calculate the confidence interval, which is sample statistic plus minus critical value into standard error, which is 4.78. So we get the range here, which is 127.9 to 146.37. So the population parameter is going to be between this range. This is the range of confidence interval with 95% confidence, since we know that significance level is 5%. We can say it in either way. Now let us move to the next slide. Here we are planning to discuss a new concept called p-value. This is another way of conducting hypothesis testing. Earlier we were comparing the critical value at a particular significance level alpha with test statistic. So if the critical value was less, we were able to reject the null hypothesis, and if it is more, we are not able to reject the null hypothesis. Another way of looking at the same idea is using p-values. So instead of converting the significance level into critical value using our table and get the z-score for comparison with test statistic, we can convert the test statistic into p-value from the same table, and we can compare this with alpha, which is our level of significance. So if the p-value is less than the significance level, if p-value is less, we will be able to reject null hypothesis. We should be careful that these signs are getting reversed here, since we know for a low p-value the statistic will be higher, for higher p-value the statistic will be lower. That is why the relationship changes here. So it is clear, if your p-value is lower than the significance level, then we will be able to reject the null hypothesis. For example, if the p-value from our test statistic comes to be 2.45% or 0.0245%, then at 5% significance level, we will be able to reject the null hypothesis. And even at 3% level, we will be able to reject the null hypothesis. But if we take alpha equal to 1%, then we will not be able to reject the null hypothesis, since our p-value is higher than 1%. So this is basically just the another way of solving the same problem. The only difference is, instead of comparing critical value, that is z-score based on the significance level and the test statistic, we convert both of them into p-value. This is significance level, this is p-value of statistic. So we can compare the probabilities. Both of these are the probabilities. That comparison will give us the same result. Now let us move to the next slide. Here we are looking at various test statistics based on the given cases. For example, if we want to compare the population mean with a number when population variance is unknown. We already know that if population variance is unknown, we use t-test, t-statistic instead of z-score, but the sample size has to be large enough. Or if the sample size is small, then population should be normally distributed. One of these conditions has to be satisfied. If the population is not normally distributed and the sample size is also very small, less than 30, in that case we will not be able to conduct test. We will not be able to conclude anything from the test. So the formula for t-test statistic is going to be the same. N-1 is the degree of freedom, x bar is the sample statistic, mu is the population parameter. Instead of sigma in case of z-score, here we are using S, which is sample variance, sample standard deviation, n is the sample size. Let us take a few other cases for test statistics. Suppose we are testing for the population mean when population variance is known and the sample size is either large or the population is normally distributed. So we conduct the z-test. We have already seen the formula x minus mu bar by standard error, which is given by sigma by root n. Here sigma is given for the population. So this was the simple case. Let us look at few other test statistics. Now here's the case where we need to calculate test statistic where we are testing the difference between two population means. Earlier we were comparing the population mean with a number, say 0.5 or some other absolute number. But here we are comparing two population means, mu1 and mu2. So two populations are involved in this case. Assuming that data is normally distributed and population variances for these two populations are unknown, they are not given, but they are assumed to be equal. Since they are unknown, we are conducting t-test and the data is already normal distributed given. But the variances are assumed to be equal. So for this case, we are conducting a specific t-test which is called pooled t-test, which is a variant of t-test. Here we are calculating the pooled variance of the sample. This is the formula where n1 and n2 are degree of freedom for both the samples. Overall degree of freedom for this t-test is going to be n1 plus n2 minus 2, or we can simply say n1 minus 1 for first one and n2 minus 2 for the second one, n2 minus 1 for the second one. We just add it up, it will be n1 plus n2 minus 2. This is the formula for SP which is used here. N1 and N2 is the sample size for both the samples. X1 bar, X2 bar are the sample statistic, that is sample means in this case for both the samples. Mu1, mu2 is the values which we want to test. They are basically population means for both the populations. Now for testing we will have a critical value coming from level of alpha, significance level. If our test statistic is greater than the critical value, we will reject the null hypothesis as usual. If the sample statistic is greater than critical value, we always reject the null hypothesis. The same we are going to follow here. Now let us look at another case, the variation of the simple problem. Here the objective is to test difference between two population means. The difference is, though the populations are normally distributed, the population variances are unknown and unequal. The only difference with the previous case was where we assumed the variances of both the population to be equal. There we conducted pooled t-test. But where we have variances unequal, we conduct Welch t-test. This is again a variation of t-test. Since variation is unknown, we are using t value instead of z value, and since the variances are unequal, we are using Welch t-test, where we are using the value of sample variances instead of calculating a pooled variance, and degree of freedom used for this t statistic is complex. It is calculated through this formula. In the previous case it was simple, n1 plus n2 minus 2, but here it has to be calculated based on the sample variances and the sample size. Again, if the t statistic is greater than the critical value, which is calculated based on the significance level, we reject the null hypothesis. Now let us look at one more variant of the t-test, which is called paired t-test. This is the statistical test which is compared for the differences in dependent items. For example, we are comparing the change in dividend policy after change in tax laws. So in this case, we do not have many companies. We have one single company and we are looking at the dividend before and after. So everything else is same except the effect. So in this case, everything is same since the company is same except the impact of tax laws. So that is the only factor which is changed here, and we are looking at the dividend before and after. So for such kind of cases, we make a pair. So if there are say 10 companies A, B, C, D, E, we are comparing the dividend of company A with the dividend of company A before and after, not with the company B. So we make these pairs and take the difference, and then we have these differences D1, D2, D3, D4, which is our sample. This is our sample. This D bar is nothing but the average of these differences of a particular sample. Mu naught is the value of population mean difference which we want to compare, and SD bar is standard deviation of this difference in the sample. Degree of freedom is again n minus 1, where n is the number of elements in our sample. So this is how we calculate T statistic, D bar minus mu naught divided by SD bar. So based on this we can calculate T statistic. Based on alpha we can calculate critical value, and if T statistic is higher then we will reject the null hypothesis. Now these were the few combinations of T test. Let us look at some other test. Chi-square test. This test statistic is used when we are comparing the population variance with an absolute number. For example, there is a population and we need to test that the population variance is greater than say 0.3. So if this is what we want to test, this is our alternate hypothesis, H naught is sigma square is less or equal to 0.3, our null hypothesis. So for this kind of test we need to calculate the chi-square statistic. The Z test and T test were for the calculation of mean, and for variance we are using chi-square test. In this, S is the sample standard deviation, so S square is our sample variance, mu naught square is our hypothesized variance. So suppose in this case we have collected a sample which has a standard deviation of say 0.35. We can put these values here, mu naught square from sigma naught square from this, which is 0.3. Degree of freedom is n minus 1, where n is the sample size. We can calculate the value of chi-square. Then we have a table where we look at the critical values of chi-square from our significant level alpha, and we compare with the chi-square test statistic. If the value of test statistic is higher, as usual, we will reject the null hypothesis. Now let us look at the another case where we have two population and we are now let us take the another case which is the variant of the same case, where we have two population instead of one, and we are making a comparison between the variance of the two. For this purpose we have to use F test. Earlier we were comparing the population variance of 1, which was sigma square, with a number which was an absolute number. In this case we are comparing the variance of two different populations. So we have two samples, we have two variances of these samples. For example, S1 is large sample variance and S2 is small sample variance. So this is the convention. We have to put the larger one in the numerator, smaller one in the denominator, and the degree of freedom for F test are going to be different for the numerator and different for the denominator, which are n1 minus 1 and n2 minus 1. So these two sample sizes could be different. There might be n1 number of elements in sample 1 and n2 number of elements in sample 2. So this will give us the value of f statistic. From our significance level, we can look at the critical value of f from the f distribution table. Then we compare it with the f statistic. If it is greater, we reject the null hypothesis. So these were about the parametric test we talked about. Let us move to the next topic. We are comparing the parametric and non-parametric statistical test. As we have seen, in the parametric test, we are concerned with the parameters. For example, in z-test, t-test, we were comparing the mean of the population. While in the case of chi-square test and f-test, we were comparing the variance of one population or of more than one population, but we were concerned with the parameters. And the validity of a particular test is based on certain assumptions. For example, if the variance of the population is given, we are using z-test. If it is not given, then we were using t-test. And if there are two populations involved and their variance is assumed to be equal, then we were using pooled t-test. If they are assumed to be not equal, then we were using Welsh t-test, and so on. So there were various assumptions. But if we talk about non-parametric test, the data does not need to meet any distributional assumptions. We do not need to assume that the data should follow one particular type of distribution. In those cases, we use non-parametric test, where the condition of normality or other particular distribution is not met. In these cases, the data is given in terms of ranks instead of values, and even hypothesis does not involve a parameter, unlike the parametric test. That is why they are called non-parametric test. The detailed cases of non-parametric tests are outside the purview of this program, so let us not get into those. Now let us take a few questions.